Today our speaker is Andrey A.Krutov from Charles University. He shall give a talk on non-integrable distribution with infinite dimensionally superalgebra of symmetries. So please, Andrey.
Thank you very much for announcement and for a possibility to give a talk. So this is some work almost finished. So the preprint is already on archive for quite a while with Dmitry Laters from Stockholm and Irina Mikhailovna Shepechkina from Moscow. So I will speak about two problems. One has a geometrical nature. Another one will be more algebraic. So motivation. First, we want to study different distributions. On some supermanifolds. I will explain what is supermanifold later. In particular, non-integrable distributions, and study the algebras of symmetries. Basically, subalgebras of algebra of vector fields on our supermanifolds that preserve given distribution. We'll give all details later, more details. So this type of construction usually works perfect in the setup of some Cartan geometries, parabolic geometries. You can associate some nice PDEs to that and do a whole bunch of things. And from this point of view, we want to have some classification results, have some simple objects, some simple distribution, meaning that the algebras of symmetries in our case will be first simple and second infinite dimensional. And the choice of this algebra setup is motivated by the classification of Lie superalgebras over some algebraically closed field, which is not necessary of characteristic 2, or characteristic 0. So it could be even characteristic 2, so it should be a prime number. Everything is done over C for Lie algebras and Lie superalgebras. There is a nice classification of finite dimensional guys up to characteristic 3 in the Lie world. In the Lie super world, you have some conjectures, and for infinite dimensional guys, it's still not clear what should be a nice list of examples. But as I will briefly recall what is going on, it turns out that when you go to the positive characteristics or to the Lie superalgebras, it is easier to classify first infinite dimensional guys. And then there is some regular procedure from which you can obtain finite dimensional simple guys. So this is a mysterious motto, but this is why this setting is interesting in our case. So let me start. I will give you, first of the talk will be just long exposition what is going on. I will give some definitions, and in the end of the talk I will show you one of the examples that was proclaimed in the paper. So the paper is about some classification results. The classification results are long and boring, but I will try to explain you what is going on and then show some scary formulas. All right, so now I need to move to the I want to give some definitions to connect these two worlds, my geometry and my algebras. So I will need the notion of this a closed of primitive subalgebras. So a closed subalgebra that I will denote L0. This is my Maskill L of some Lie algebra L, which is first of finite codimension. in my Lie algebra L. First, I will formulate everything for Lie algebras and usual manifolds. Then I will jump quickly to the language of supermanifolds, but you will see that it will be easy because I will use language of sheaves.
Sorry, you didn't assume an Lie algebra is a finite dimensional.
No, no, no. The most of the story is this will be something infinite dimensional. And contains no ideals of L, well, except the trio one. I need a comma here. Is called primitive. Oh, sorry, it's called fundamental. And then it will be primitive if it's maximal. If it's also a maximal subalgebra. The point is to consider such construction from the geometrical point of view that this condition tells you that the corresponding group, if you will integrate, will act transitively. So it will act transitively on your corresponding manifold, or that this subalgebra will not admit some invariant foliation. And a long time ago, Elie Cartan classified such objects. In 1909, well, he suggested the least, and I will explain that his classification was correct, but the proof had a gap that was fixed later. So he gave a complete classification of primitive infinite dimensional subalgebras of the Lie algebra of vector fields on Cn. And in what follows, I mostly will be interested in some nice distributions. So that means that I could do everything local, don't care too much about the topology of my manifold. So every time when I speak about some manifold or supermanifold, you can think about Cn, k to the power n, so on. Or when I go to positive characteristic, everything is local here.
So I guess you mean holomorphic vector fields on Cn here, or?
Well, yeah, it will be, yes.
Holomorphic, okay. Sorry, just for my information, the maximality conditions here is an ideal.
As an algebra, a subalgebra.
Okay.
You have a chain of subalgebras.
Okay.
And it's a maximal proper subalgebra.
Would you always have?
Sure.
An extension of a subalgebra to a maximal proper one?
Yeah, yeah. Well, if it's maximal, if it's subalgebra, then it's either maximal or contained in some subalgebra, or contained in some maximal. You have a chain.
Okay. No, but in rings, the reason there's a maximal ideal because it always has to exclude the unit element. But in Lie algebras, there's no unit.
You don't have a unit. Your unit is zero, so and it's always there.
But you still always have maximal proper subalgebras.
Well, if it could be, well, you know, we start with some subalgebra, right?
Yeah.
Which is proper. It has finite.
Okay.
It has finite.
I see. Okay.
So
it already has this property.
If you have it, then it's
Okay.
either maximal or contained in some.
Okay.
So there is no such a problem here.
Okay. All right. Thanks.
Thanks. All right. So let me explain the Cartan's idea, and we will see how it's connected with distributions. Of course, the classification is very simple. It's either divergence-free vector fields, contact vector fields, or Hamiltonian vector fields. This is simple, guys. Well, modulo some low down. some low-dimensional examples. So the basic idea was the following. We should switch from the filtered situation to the Z-graded. So we should look at some Z-graded Lie algebra. It will be negative. It will be of this form. So the depth of my grading is -1, which is associated, so is Z-graded. To the natural filtration of my Lie algebra L, given by the order of the vanishing of my vector field at the origin. So you can think about it now because we look at the holomorphic. You can think about the polynomial inside and so on. It goes a bit more funnier when you allow Laurent polynomials, but it's outside the scope of this talk. And in what follows, my curly letters will be for filtered guys. Gothic letters will be for Z-graded business. So then you need to find such Z-graded algebras with the following condition, that the isotropy representation, G minus, tropy representation of G0, and G0 here you can think about it as a stability algebra that acts by derivation and preserves the degrees, should be reducible. So passing from this filtration to this Z-grading, you reduce the problem to finding some such objects, and this is quite technical and you can solve it easily. Now let's move further and see what will be the... take here as a definition, this is just minus first component. So it's coming from the fact, the same analogy when you have, for example, homogeneous space, and you have isotropy representation that models the tangent space. Okay. So the problem, this problem could be solved quite easily by the standard methods, but Cartan's approach had a gap. The gap was the following. So the gap. It was not clear how to reconstruct the Lie algebra of contact vector fields. So we have our contact form, and just for on 2n plus 1 dimensional manifold. So remember that it's a vector field on this Cn. This is my notation. So it's my Gothic K. This is my attempt to write a Gothic vect, such that the vector fields preserve the contact form. And the contact form in the coordinates, of course, could be written like this. So you choose special coordinate C and then the pair, so as usual. As it will know that this guy has a filtration too, depth 2 filtration, because if you look at the generating vector fields, then in degree -2 you will have 1, in degree -1 you will have PQ, and this is not covered by the Cartan setting because this will be not solution, and this problem existed for quite a long time until Boris Weisfeiler in 1968, in his short paper in functional analysis and its application, suggested the following way how to overcome this obstacle. So he proposed the following method.
And when you were talking about contact vector fields, you're really those which represent the contact form, not the distribution.
Well, in this case, it will be the same.
So, sorry.
Will be the same. On the C2n plus 1, it will be. You will get some difference when you will get some topology. And it's not the same situation with Hamiltonian and symplectic vector fields. There it's a bit different. So here it's much easier. All right. So what was Boris' solution? So he proposed to do the following. He narrowed the subspace L minus 1 in my filtration to the space of sections of my contact distribution. So in this case, D will play a role of a contact distribution, then we will extend it to any distribution. So consisting of the vector fields that lies in my Lie algebra of all vector fields, which are tangent to my distribution. So they're just subsections, they live there. And then he defined the negative part inductively. So he started with, we'll have minus first guy, then we'll have minus 2 guy, which will be just the commutator of L minus 1, L minus 1, so on, until it will stop somewhere. Let's say degree minus D. So every time we take a commutator with L minus first part and the previous. And D here will be called the depth of filtration. So this filtration later will be called Weisfeiler filtrations. I'm doing this time. Okay, that's fine. All right. Then, if my L is a primitive Lie algebra, of vector fields preserving my distribution, then my distribution will be bracket generating. Meaning that the minus first part in filtration will give me everything. If you will consider now the associated graded, so this filtration and the associated graded algebra are called Weisfeiler filtration and Weisfeiler grading. Or grading. Or sometimes I will just say that it's W graded, W filtered, for simplicity. Then, basically, the gap in the Cartan's proof was filled in the paper by Boris. But later, Guillemin gave a detailed proof in the paper in Journal Differential Geometry, adding the whole details. So I think Weisfeiler paper about 3 or 5 pages long, as it's common for functional analysis and its applications, and the Guillemin's paper is, I don't know, 60 pages. All right, so this is a setup in which we will work. So we will be interested in these W filtrations by the following reasons. So they will provide us examples of non-integrable distributions, because they will come from the fact that we'll have depths of filtration greater than 1. Then we will see them as a tool to generate new simple Lie algebras. Okay. Now we should where's the blackboard? Yeah, that's the right moment to ask some philosophical questions.
I think I didn't quite follow the original filtration that Cartan defined. So he started with vector fields on Cn.
Yes.
And then
you look at the vector field.
Yeah.
You look at the origin.
Yeah.
And you look at the order of vanishing of this vector field.
Okay. So it's just a way of ordering them about an arbitrary point.
Yeah.
And G-1 was were the vector fields that were not vanishing at a point.
It will be everything.
Sorry?
It will be everything. Wait. I'm lying to you. Yes, I'm not lying to you. This is everything. G-1 is all of them.
But L-1 is the smallest one.
L-1 is the biggest one.
Not how you wrote it.
Yeah.
Okay. Okay. So these should be reversed. The inclusion should be reversed.
Yeah.
Okay. Okay. And what about the negative direction?
For negative, I wrote it correctly.
Okay. So there it is correct. Okay. All right. So in negative direction, you increase. You make your Lie algebra bigger.
Okay. Wasn't quite enough. Okay, now how it's connected with the distributions. So we can. This I defined for contact distribution, but we can go to a general distribution on my manifold in the following manner. So, distributions. So let M be m-dimensional manifold. And I will describe the flag associated to my distribution. So the flag is described by the space of sections, and in general now when I will speak about distribution, so they usually treat it as a sub-bundles of a tangent bundle. Since I want to work with the super stuff, you can think equivalently as a tangent bundle as a sheaf of sections, and then it will be sub-sheaf, which is locally free and have a locally free factor. So everything will be sheafified. It's very easy, and then it produces no problems for superization or go into the positive characteristics. So we will look at the span of the sections of degree -1 of the bundle di spanned by the brackets bracketing spanned by the bracketing of less than I copies of sections of my distribution d minus 1. So you're going up, 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 up. So that means that we can define it as follows. Absolutely in the similar manner as we did it with the contact distribution. So now I will need to assume some regularity condition, and they have the following. So first, the distribution is called regular if for every point on the manifold, the dimension of these filtered components are the same. Otherwise, situation becomes a bit more difficult. So we'll have some singularities.
Constant as a function of n, not of I.
Yeah. Well, here I am, sorry for poor notation maybe. It's a dimension, but you can look, you look at this thing, so dimension of this space at the given point, and this should be a constant.
Sure.
And then it will be mi.
And it could depend on I. Not,
Yeah.
Not true.
Yeah, let me do this. Okay. Now we consider only complete distributions. So a complete regular if the sections generate the whole TM. So if you will have enough brackets, then you will get the whole tangent space. And should I recall what is the integral manifold integral distribution? So as you can imagine, if you have a distribution, if a submanifold of M is called integrable if its tangent space is just given by D. And we will be interested in non-integrable distributions in what follows. And non-integrable, so I think it was due to Hertz a long time ago, who calls them non-holonomous. Then the modular spanning will be non-holomorphic, non-integrable. This is all synonyms, and as I understand, one of the two my favorite examples is a cat falling, because cat should fall on the poles. So it will be an example of some non-integrable system, non-integrable distribution. Also, cruise control. When you set up your length of your, how it's called, velocity vector, so it should be on some n-dimensional sphere. Yeah. So let's move further, and let's define the symbol algebra. Graded TM corresponding to D will be denoted as follows. So this symbol algebra is nothing but, so it will be some graded Lie algebra composed of the graded components. Well, when these graded components, so the sections of these things, are just given by the quotient. And in what follows, we will assume the following assumption. It's again some regularity. So we should look at the slack of the sheaves of our sections of our distribution at every point. It will be some z-graded subalgebra. So we take a point, we look at the corresponding stalk of sheaves of our distribution at this point. It is some z-graded subalgebra. This species also depends on star, such that the dimension of our guy is the dimension of M. This is our completeness condition. So we generate the whole tangent vector, tangent bundle. And then we suppose that let G0 be the subalgebra of derivations of G minus, which preserves degree. So our next assumption is that G0 acts irreducibly on G minus 1. And we also assume that all these Lie algebras are isomorphic for every point. So I could drop the dependence from the point. This is again, so this condition just some local coordinates in some chart over our manifold, and because we assumed all of these regularity conditions, it doesn't matter which point we choose, the system of local coordinates that will be compatible with our distribution, and then this system of coordinates will give a natural z grading by these formulas. So you take the coordinates that will be compatible with minus first component, then you add coordinates that will give you minus second components, and so on. You go in the positive direction because when you switch to vector fields, your grading will be in the opposite direction, so that's fine. And let's call the collection of these dimensions that we defined before, where there was mi's that doesn't depend. These guys, the growth factor of our distribution. Okay? And this will be our tool to study, to produce different new distributions from different gradings. And the Lie algebra of vector fields with this grading will be denoted by V. I absolutely don't know how to write on a blackboard a Gothic V, so this is my best attempt. Sorry. Perfect. Now, with this setup, I want to speak about the Cartan prolongations. And first, recall what is the transitive actions to Lie algebras and Cartan prolongs. Prolong here means that it's a result of a prolongation. So, if we have a primitive subalgebra, we can consider the corresponding graded version of it. So, if the graded algebra associated to the primitive Lie algebra is primitive, then we have the following conditions. So first, the minus first part will generate the whole negative part. And second, if you will have an element in the non-positive, non-negative part, such that if you will take a commutator of this guy with every element in the minus first component, this will implies that this is zero element. All right, and sometimes these guys called also transitive because they correspond to the transitive actions of the corresponding Lie groups. And again, this is the same problem with the non-holomorphic distributions and non-integrable, just coming from two different directions. So the maximal transitive Z-graded algebra has this non-positive part given by, so we take our primitive subalgebra, negative part of our primitive subalgebra G minus, and G0 is degree preserving derivation of G minus 1, is called the Cartan prolong. It's called or complete Cartan prolong. Now you can consider instead of G0 some subalgebra of it. So let us restrict our attention to some subalgebra. So let's S be a subalgebra of G0. Then we can look at the partial, not a partial, but just Cartan prolong of the pair. So it will be defined like that. So this means that now instead of this non-negative, non-positive part, we're choosing G1 and S. So obviously the Cartan prolong is completely determined by minus first part, and Cartan prolong is determined by a pair of minus first component and S, subalgebra of the grading preserving derivations. This is very important tool in Cartan geometries, for example, or parabolic geometries, and in the classification of Lie algebras and Lie superalgebras, it's a nice object. Let me give you a couple of examples. There is also notion of a partial Cartan prolongs, but I will not speak about it today. So as a test or small exercise, I could give you an example. So suppose I take the following G minus part. It's just a abelian Lie algebra of dimension n, whose elements are concentrated in degree minus 1. Then I'm trying to ask you what will be the Cartan prolong or algebra of preserving derivation of degree 0. It's very easy. So n-dimensional abelian subalgebra, look at the derivations that will preserve this grading, and the grading everything in degree minus 1. Well, the answer, it will be GL. So And as a module, it will be just tautological representation. And if you will take the complete Cartan prolong, then as a result, we will get the algebra of vector fields. Another example, if instead of taking the full Cartan prolong, we will take a Cartan prolong of the pair of standard representation and SL, and then of course it will be divergence-free vector fields.
You get all vector fields or just vector fields?
Here you will get all vector fields. Well, it's isomorphic, but I'm speaking now.
Just at one point.
Here star means that it's not a point, but a result of a prolongation. So it will be vector fields on Cm.
Are you doing it at all points?
Well, no, this is quite abstract notion. It doesn't involve any manifold. So to be fair, I need to put a tilde here. And this, maybe it's a better notation, but this star doesn't mean that it's a point. It's just saying that we take a pair and take some operation. Okay? Then the same you can do with Hamiltonian vector fields. Sorry, I should have gone in opposite direction. You take standard representation and your symplectically algebra. And for contact vector fields, it looks a bit more complicated. You take Heisenberg Lie algebra of dimension 2n. It will be now graded, and it will have two graded components. Minus 2 graded component will be the center of this guy, and the rest will live in the degree -1. And you take my symplectic Lie algebra will act naturally there, so on -1 component it will be just identity, and the -2 component will be trivial module. And then if you will take the Cartan prolong of this guy, you will obtain my contact vector fields. Note that here, and here, this is abelian Lie algebras. Here, this is not abelian, but some solvable. Perfect. So we can move further. So we already see that starting from some special gradings, we can obtain a lot of, well, actually all simple infinite dimensional Lie algebras over C. So the same goes to, the same approach is used in the classification for super guys and in positive characteristic. And probably the final accord about the motivation from the geometrical part. There is a result by Vershik and Gershkovich, which stated the following. So they formulated it in very geometrical manner. I don't have a time to give a full formulations, but more or less, if you assume some regularity, then as infinite dimensional algebra of symmetries, you can get algebra of symmetries of the following things. So it's either contact distribution or angle distribution. With the following gross vector, 3, 4, 2, 3, 4. And only these two objects will give you infinite dimensional Lie algebras of symmetries. And you can notice that in this case, you will get the contact vector fields. In this case, the Lie algebra will be non-simple. And this was original motivation for our story is that we wanted to generalize this result to the case of super Lie algebras and super and regular Lie algebras in positive characteristics. And now I could give you, so this was the end of the introductory part and the motivation explaining why you can think about the geometrical problem and algebraical problem in the same manner. So there is many connection between distributions and the corresponding Cartan prolongations and Weisfeiler filtrations and gradings. So now I will briefly recall the basics of supergeometry, and you will see that basically everything will work in the same manner there. And in the last minutes of the talk, I will give an example how we was able to find new W filtrations or gradings starting from such type of story. Of course, there is many technical details that I'm hiding under the desk, but at least the main point that I want to make is these connections between W filtrations gradings and the corresponding non-integrable distributions. So Lie superalgebras and supermanifolds. Usually, if I had more time, I will give a more categorical definition of a Lie superalgebra. But here it's just that two-graded vector space, which zero part is Lie algebra, and which has a bilinear bracket, which satisfies the skew symmetricity condition. And the graded Jacobi. To go into positive characteristic, you should employ something more difficult, and I refer to our paper and references in it when we explain everything carefully, but to feel what is going on, this will be enough. And supermanifolds, so it's a Lie superalgebra. And for supermanifolds, I will use the definition that initially Berezin and Letas was using. So I will define supermanifolds as a ring space. So we start with M, be a Hausdorff. Topological space. Some sheaf on it, which locally looks like this. So if I look at some domain of my topological space, this sheaf is isomorphic to the sheaf of smooth functions there. So I'm assuming that this, my Hausdorff topological space, is secretly a manifold. Or if you're in the holomorphic category, then it's holomorphic functions tensored with some exterior algebra. And then the dimension of it is dimension of n, dimension of x. So the pair is a supermanifold. Then we want to speak about the different notions like distributions. To speak about the distributions, we need a tangent vector bundle. What is a tangent bundle here? It's, of course, the sheaf of derivations of our structural sheaf. if you want to speak about covectors, you take a dual sheaf. What is the distribution? So if it's a sheaf of submodules which is locally free and has a free component, free direct summand. And because we're now speaking about the sheaves, everything that I said, even without adding any signs, will be directly transferred to the super world, and consequently, it's also very easy to work on the regular manifolds. For the next example, I will need I will need a beamer, and I think I remember how to do it. So I will start sharing here. It's Control L, right? All right, perfect. I want to give an example when we got some new distributions from already well known. So this is a bit involving example because all non-trivial examples require some big computations. So we should go to the characteristic free and consider the Brown algebra. So this is a Lie algebra with the following Cartan matrix. Then from this Cartan matrix, Lie algebra with a Cartan matrix, we want to consider some, we want to cook some some negatively graded Lie algebra. So let us introduce a grading on this Brown algebra by saying that our simple first and the second root vectors will have degree 0, and the third guy will have degree 1. So maybe I could use this guy, right? Is it working? No. I should click here. Okay. I think the pointer works, right? Yeah. Okay. Yes, this is magic, and this is why it's hard. So then I will take the negative part of our Brown algebra in this special grading and consider and it could be realized in the following vector fields on a 10-dimensional variety. So here my vector fields, they here just to scare you, but they also tell you the dimensions of the homogeneous components. And what is crucial here, that there is a nice theorem by Yamaguchi that if you go to the characteristic 0 and or a complex number, if you will take the Cartan prolongation of such negatively graded Lie algebra, then you will recover the original algebra. In super case and in the positive characteristic, this is not true anymore, and the corresponding Cartan prolongation is called deep Scriabin algebra, and it's quite big. So, and obviously it gives us example of some non-integrable distribution because the depth of this distribution is -4, right? We have something non-zero in degree -4. Now, how to study different, using some technical results that I refer to the paper and the previous paper by Letes and Irina Mikhailovna, what we can do. First, we know that our Lie algebra now realized as a vector fields, subalgebra vector fields acting on some 10-dimensional variety. We can look at the corresponding Mauer Cartan forms, and they are written here. Then, as I explained, our gradings corresponds to the different gradings on the algebra of functions, some on different coordinate systems that adapted to our distribution. That means that this malware Cartan forms in this coordinate should be new batteries as a...
Yeah, okay, now this sounds...
All right. Okay, so this is one of the solutions of the admissible grading, regrading of this algebra. And here we have degrees of our original degrees. It turns out that, let's look at our formulas. So we said that degrees of the first, second, and the fourth coordinate will be 0. Then the rest of the guys will have degree 1, and the U10 will have degree 2. So, and let's count 1, 2, 3, 4, 5, 4. So that means that we can also realize this thing as a subalgebra over contact vector fields, because this type of grading corresponding to some contact vector fields. Here, that means that you can look at that, the corresponding generating vector fields. So, and this is vector fields in the corresponding negative part. Then you can look at the G0 component, which is a maximal, which is an algebra of derivations which will preserve the degree. Or you just look at the 0 component of our deep Scriabin algebra with this new grading, and this will be something horrible. If you look at the corresponding vector fields, so again, this is the degree with original grading, this is a horrible vector fields, but these guys looks much nicer in the contact subalgebra. You look at the generating functions, and in this way you can derive some results about the structure of this algebra, which again I will refer to the paper, they're quite technical. Then we can have another W-grading corresponding to this solution. Unfortunately, this is not of a contact type, because this solution has something in degree minus, in degree 3. Again, this is correspond to non-integrable distribution because we have not only once. Then the regrading corresponds to this guy, so this will be the negative part, and this will be the degree preserving derivations. And it will be another regrading of our deep Scriabin algebra, so it now could be realized on 11-dimensional variety. And this will, using some arguments, we can prove that this exhausts all possible Weisfeiler regradings. So two of them will be, each of them will be a corresponding non-integrable distribution. So this is one more example when we get something new. And to go further, I refer to the paper. It's about 60 pages because we consider different known simple infinite-dimensional guys, look at the different W regradings of them, and obtain some new regradings, new new non-integrable distributions in the positive characteristics explicitly for some Lie algebras and super Lie algebras. And They will be also the source of some new finite dimensional simple Lie algebras, but this is another story and another project. So thank you for your attention. And sorry for technical problems.
Thank you very much, Andrey, for your exciting talk here. So that is, how to say, you mentioned about the rep of the garden.
Mm-hmm.
So when it was discovered?
Well, the Lie Cartan wrote the classification of primitive in 1909, but with a gap, with the contact distribution.
But who noticed it?
I think it was maybe clear from the beginning. It was clear from the beginning, I think.
From the beginning, so that he corrected mistake or no?
Mistake was only corrected by Weisfeiler.
Yeah.
So Cartan gave the right list, but the proof wasn't there. And the Weisfeiler note, I think the whole idea is there, and more detailed exposition in the Gilliman's paper. And then these tools was a bit not so important later because, well, for Lie algebras over C, you always will have only one W grading. But then Alexeyevsky, Leitos, and Shepachkin in 70s, I think already, or 80s, observed that in super case you can have a different W gradings. And the importance of that was later observed in the classification of positive guys.
Is there some question? So there something maybe related to I think that there is a lot of school indeterminates, right? Something that Krutov asked, I remember, he said that that method is, of course, good, famous, but there are another guy, I don't know what his name, is a more natural.
Well, yeah, it's also connected to this business of Slovak chap Peter Micher on these parabolic geometries. But for Cartan's method of a moving frame, this Cartan's prolonged is one of the tools when you want to investigate the symmetry structure. So the Cartan's method of moving frame will produce you some data from which you can consider the Cartan prolonged. I should speak in the microphone, not use it as a pointer, and then yeah. So this is. Well, in Vinogradov, as being one of the person from Vinogradov school, I should know because I'm certificate great grandkid of.
He was kind of the ascendant of the you have some relation.
He's my scientific great grandparent. But that as much I could say. When it's basically provide you one of the tools to give you symmetries of your geometrical structure.